Great, thanks and welcome back. So I'd like to get right into introducing our next speaker. It's Blaise Egan. He's a statistical advisor to senior management across the whole of BT Group. Now, I don't get statistics, but I think Blaise has probably forgotten more about statistics than most of us will ever know. He's been involved in a number of high-profile legal cases where deep knowledge of statistical science is required. He holds a degree in mathematics. He's got a master's in statistical application in business and government. He's also got a master's in Bayesian Statistics. For those of you that don't understand Bayesian Statistics, Google it. It's actually quite a fascinating topic. So on that note, Blaise, I'll hand over to you.
Hello there. Hope everybody can hear me. I'm not using a virtual background today, so I've got my ceiling light giving me a halo. I've often been called a statistics guru, but I don't really have a halo. This talk is really about a kind of historical perspective. How do we get here? So there are multiple components to data science. Computing and domain knowledge and statistics has been one of the oldest. So statistics is a relatively old subject compared to computer science. It goes back about 300 years or so. I just want to show how some of the ideas that we're using got here. So, statistics takes its name from the fact that it was what you used to have to teach the monarch in order to run the country. And there are a couple of different parts to statistics. One is the bit that I think that most people find kind of boring, which is descriptive statistics, just tables of information that are just describing what we've got, how much of it, where it is, and so on. The bit that's a bit more interesting is statistical inference. So this is how we're drawing conclusions from the data. Now that involves mathematical models. So you have to have some kind of model of what's going on underneath the data that's giving rise, so the data generating model, what's giving rise to the data that we see. And that allows you to make some inferences, including inferences from noisy data. So there's a whole mathematical theory to do with how do we deal with uncertainty. And that is what statistics brings to the table, the ability to deal with uncertainty. More recently, people have been exploring things like exploratory data analysis, which is now that we have powerful tools, we have a much better ability to explore the data and get familiar with it, particularly when we've got large quantities of it. So this idea of probability, which is the mathematical description of uncertainty, how did that come about? Well, it didn't come about because pure mathematicians thought, let's have a method for dealing with uncertainty. It came about because of gambling. So there was a professional gambler called the Chevalier de Marais, and he was a very experienced gambler. And he wrote to a great mathematician, Blaise Pascal. I'm not named after Blaise Pascal, who was one of the greatest mathematicians of the 17th century. He invented a calculating machine, an adding machine, a calculating machine, and he was influential. He thought this was some interesting problems were turning up in gambling, so he discussed them with his mates. And his mates included Fermat. And so you've all heard of Fermat's last theorem. Fermat was a jurist, a judge by day, but a brilliant mathematician by night. And they discussed several issues. And in the process of discussing that, they actually formulated the ground rules for probability. This was a huge, huge advance at the time. So I've got a hidden slide in here. If you look at the slide deck, you'll see one of the calculations that helps out Marais. I haven't time to go into the details here, but there's more in the Wikipedia. Significance tests are something that are very common in applied work in data science. In the statistical community, they've fallen out of favor, basically. We're kind of encouraging people by saying, don't do that, partly because they're very easy to misunderstand, and partly because they encourage binary thinking. It's not necessarily the way to go to divide things into this is statistically significant, this is not statistically significant. But nonetheless, they have historically been very influential, and you'll still see them very widespread. There are better methods about, I would advise you. So John Arbuthnot noticed, he looked at the birth records for London for 82 years, and he noticed that in every single year, more males were born than females. Now, if you thought the ratio of males to females was naturally 50%, I'm afraid you're mistaken. It's well understood these days that about 105 males are born for every 100 females. But here, Arbuthnot looked at this ratio and said, well, what's the chances that if they were equal, what's the chances that you get 82 years consecutively with males more than females? And he worked out that probability. And that's what we would now call a t-test, and that would be called a p-value. And it's tiny, so he proved his point. The Bernoullis were a family of Swiss mathematicians. Johann was as great as Daniel. But Daniel looked at the idea from Pascal that the value of a lottery ticket is the value of the prize multiplied by the probability of winning. So he took this idea and he came up with, so he exploited this idea of expected value. And he wrote a very interesting paper, which I recently read, where he considered a ship going from Amsterdam to St. Petersburg in winter. This is a very risky thing to do because of the weather, and there's about a 5% chance you could lose the ship. So he works through the problem of how do you work out whether it's worth taking out insurance or not. So this whole idea of utility, which is something that greatly influenced the economics literature. And the St. Petersburg problem is also something you should Google. He also did other things. I mean, apart from probability and statistics, he's influential in the design of aerofoils. Every pilot will tell you that Bernoulli's principle is what keeps airplanes up. Carburetors, conservation of energy, generally a brilliant man, but decision theory arose with him. More on probability. Pierre Laplace was a brilliant mathematician in the 18th century, covered a wide range of things. He wrote Mécanique Céleste, which is a major textbook on celestial mechanics. He developed probability and Bayes' theorem in particular. Now, Bayes' theorem is, in one sense, just a simple algebraic manipulation that allows you to turn conditional probabilities around. If you have the conditional probability of x given y, and you want the probability of y given x, Bayes' theorem is the thing that you want. But it turns out that people realize that actually Bayes' theorem has a much deeper significance because it is the mathematically correct way of learning from data, learning from noisy data, and viewed in that light, it's led to a whole different way of interpreting probability and whole new methods, which turned out to be computationally difficult until the mid-80s. He also looked at the ratio of male to female births, so he did it using Bayesian methods. Bayesian methods should really be called Laplacian methods. Florence Nightingale. I do hope everybody these days realizes that Florence Nightingale wasn't just a great administrator and founder of the profession of nursing, as we now know it. She was actually a trained statistician. She was trained by William Farr, who was the general registrar for births and deaths. She had a deep mathematical understanding, and she felt that the use of statistics was a religious obligation because God would want you to do things properly and efficiently. She used state-of-the-art methods. She used a control group when she compared the death rates of soldiers in the Crimea, in the Crimean War. She compared them against soldiers in barracks, and that idea of a control group is a crucial idea in statistics. She also invented data visualization methods to get her ideas over to politicians and Parliament. She reformed the nursing profession and used statistics to improve performance. So not just a great theoretician, but actually somebody who could put things into practice, a terrific role model for statisticians. Francis Galton, well, a huge polymath, many different things he invented, basically regression, but also things like fingerprints, terms like the standard deviation and the median, the two-dimensional normal distribution. He's out of favor these days because of his views on eugenics, I'm afraid. A lot of people were influenced by the terrible ideas of eugenics, but he did do a great deal of inventing for the statistical profession. Similarly, for Ronald Fisher, the design of experiments. How do you design experiments to extract maximum information? He promoted factorial experiments. People used to, prior to that, used to test one thing at a time. If there were multiple features that you wanted to improve, then people would try them out one at a time. We now know for 100 years that that's not very efficient. He promoted randomization in statistical experiments to remove bias and to balance the things we're not measuring. He invented the p-value method of significance testing, the correlation coefficient, hugely inventive person. Probability was finally put on a completely rigorous basis by André Kommelroth, another great mathematician who did work in a wide range of fields in the early part of the 20th century. So he actually defined probability as a measure, as a whole branch of pure mathematics called measure theory, which is basically to do with how big are sets. And it ties into all kinds of things like calculus. So calculus is counting things in it and summing things up. But by using probability as a measure, it ties it into the rest of pure mathematics. Then we come to Bayesian statistics, which began in about the mid-50s. And there were several people who were involved in this. Dennis Lindley, a very provocative character in the 1980s. I met him personally on a couple of occasions. De Finetti in Italy, Frank Ramsey, who also invented a whole branch of graph theory, and Jimmy Savage in America. These guys basically put together the modern Bayesian viewpoint from the 1950s onwards. More recently, we've got to people who are actually still alive. David Spiegelhalter, Phil David, and Stefan Luritzen. The problem was, how do you get probability into expert systems? How do you get them into computer decision-making systems? Initially, people tried using frequentist statistics, the traditional way, and Spiegelhalter and others showed how you could do it, how to do machine learning on networks using Bayesian probability, local computation, so you only have to look at nearby nodes, and Bayesian nets. Lastly, in case you thought this was a boys-only club, no, it isn't. Hugely important work done by Grace Warbar, who invented generalized cross-validation and spline function. She didn't invent spline functions, she brought them to the fore. Ingrid Doberschi on the right, she invented wavelets, and they compress data immensely effectively, and her methods, the JPEG 2000 standard, is used in AFIS, the American FBI database, which is far smaller than it would have been without her. And at the bottom, we've got Di Cook in Australia, who's pioneering data visualization. So there are a lot of great women doing a lot of great work here. Just want to underline that. There's a few references for you. That's basically it. Great. Thank you.
Great, fantastic, Blaise. Thank you very much. Once again, some fascinating insights around statistics and what's going on in that space. What I'd also suggest is maybe you reach out to Blaise as well, because I know there's a huge range of other material here that he's got from this particular perspective. We're just really, I wouldn't even say we're scratching the surface, we're kind of rubbing it. We haven't even scratched it, we're just rubbing the surface in this particular topic. So Blaise, thank you very much.